a little bit dangerous again, but
oh, really?
yeah,
Oh, I see. I see.
and it happens in Seoul, so it's different from the previous cases, which happened in the smaller cities. So yeah, so we may have
Yeah,
a bigger impact this time, but yeah.
I see. Yeah. For now, I'm mostly staying at my home.
Mm.
I just go to my office at the university like once a week or so.
Uh-huh.
So, well, yeah, I'm pretty fine with that. But sometimes my students are kind of complaining about that because they're kind of they get frustrated staying at home for the all the time.
Yeah. And they are probably like a kid, right? If they don't see the professors or parents, they complain and then want to
Oh,
meet again. Maybe.
well, maybe I don't know.
Yeah. And then I heard it's quite challenging to spend the time with the kids for 24 hours per day.
Uh huh.
Are you okay with that? I mean, I
Well,
heard that.
okay. Well, actually, the nice thing is that we have our daycare open
Oh, okay.
for these. I don't know. Well, it's from Well,
Mm.
they were closed for 2 months, like March, April. That was
Mm-hmm.
tough.
Mm-hmm.
Daycare was closed, so I needed to feed my babies for 24
Uh-huh.
hours. But after that, from May, it's
Mm-hmm.
pretty okay. So that's why I'm kind of feeling more and more comfortable with this situation because kids are in daycare and I can stay at my home.
Good, good. And then
So
you can
that
do your work.
yeah, that's right. That's right.
Uh,
Correct.
so I think people are starting to getting in.
Mhm.
But we can probably wait a few more minutes to wait for the
Yeah, sure,
more
sure.
audience. Yeah,
Yeah, sure.
yeah. These days I miss the tonkatsu in Japan.
Tonkatsu?
Yeah, I miss it a lot.
Oh yeah, yeah, yeah. You should. Yeah, after this that virus converges, you should come to Tokyo, and I can treat you
Yeah.
with tonkatsu, sure, for sure.
Okay, that would be great. Yeah.
No.
You should visit Korea again too. I
Oh
can
yeah, yeah.
bring
That
you
would be
to
great.
fugu fish places. Okay.
Yeah, that was nice. That was nice. Yeah, that's true.
Uh,
Yeah, I was pretty impressed by the fugu treatment.
yeah. You don't
That
need
that's
to give a talk or you don't need to do the physics discussions. Yeah,
okay.
I'll be happy to bring you to the restaurant.
Wow, that's great.
Yeah, yeah. So let me just give a short announcement to the audience. So please mute yourself so that the speaker doesn't have a problem. So and then we are going to wait 1 or 2 more minutes so that more audience will come in. Yeah. Um, I think a lot of people are coming in to your talk. You're pretty famous, so.
Wow, yeah, thanks so much. Yeah.
Mm,
Are you teaching this semester or next semester maybe?
yes, yeah. So I'm teaching this semester, but it's through Zoom. So
Oh,
actually,
okay.
I'm in Seoul, so I'm not in Pohang now. So
Oh, really?
yeah,
Really?
essentially, I can be anywhere I want.
Anywhere?
So yeah, perhaps
Oh.
I shouldn't be. I shouldn't talk about private things too much here because there
Yeah,
are some
everybody is hearing
students
you.
and
Yeah, maybe,
stuff.
maybe,
So, yeah.
yeah, for another, yeah, at another time.
Yeah, I don't want to give impression that yeah,
Yeah,
I'm not
well, yeah,
into,
let's check
yeah,
at another time.
yeah. Anyway, thanks for asking. Yeah.
Yeah.
So I think we can slowly start. So let me first introduce Professor Takahiro Morimoto. Actually, I don't feel I need to introduce him too much because he's already pretty famous and a lot of people knew about his papers. Actually, I learned about his works from his PhD, and then he was pretty famous from then, I think. And as a brief introduction for his career, so he got the BS bachelor degree and PhD in University of Tokyo under the supervision of the Hideo Aoki. And then he moved to the Berkeley Before that, he was also working at the weekend, but at the Berkeley, he got the some sort of prize fellowship for his postdoctoral study, which is Gordon and Betty Moore postdoctoral fellowships until 2019, and then he became an associate professor at the University of Tokyo. And he has been pretty prolific and very famous about his non-equilibrium states and the nonlinear optical responses, and also the interacting topological orders. So he has a lot of various interests, but today I think he's going to talk about his recent works on the geometrical nonlinear responses about the shift currents and the non-reciprocal current. So let's welcome the speaker, and then Takahiro, you can start to share your screen and start.
Yeah, thanks so much. Thank you for great introduction, and I'd like to thank Gil for giving me a very nice this opportunity to present a few of my recent works. So I'm Takahiro Morimoto from University of Tokyo, and I'd like to talk about some geometric aspects of nonlinear responses, especially so-called shift current and also the non-reciprocal currents. So these days, the notion of geometry and topology is becoming more and more relevant in recent condensed matter research, especially after the discovery of topological insulator. And more and more people are working on this field. On the other hand, there is a rich research field devoted to the nonlinear responses. For example, nonlinear optical effects have lots of fun. For example, photovoltaic effects can be used as solar cell, and then these high homogeneization can be used as a wavelength conversion devices. And also the nonlinear transport is a rich field, and then it can be used as a diode effect like this with a nonlinear IV characteristics. So there has been a lot of work on nonlinear responses, but not many studies focusing on the application of notion of geometry topology into this nonlinear field. So today I'd like to show you a bit of examples of how geometric phases and the geometric aspects emerge in the nonlinear responses, especially through the coupling via Berry connection and Berry phase in the curvature. So this is the plan of my talk today. First, I'd like to introduce a notion of geometry and topology in K-space very briefly. And then I'd like to present you two examples of such geometric nonlinear responses. The first one is so-called shift current, which is a geometric nonlinear response. And the second one is non-reciprocal current. That can be essentially a diode effect in a tunneling problem. Both effects involve the so-called Berry phase, and it has a geometric aspects. So yeah, let me start with a brief introduction about the general electromagnetic responses in condensed matter, which can be described by J dot A coupling. J is current, A is a vector potential of electromagnetic field. And we are dealing with the crystals, which form a band structure like this due to the Bloch theorem. So this current operator can be generally categorized into two pieces. The one is the intraband matrix element, and the other is the interband matrix element. And then essentially intraband matrix element is basically the wave packet moves according to the external electric field and carries the current. That distinguishes whether the system behaves as a metal or insulator, depending on the position of the Fermi energy. On the other hand, the interband matrix element can play some role even when the Fermi energy is lying in the band gap, because this interband matrix element basically connects the valence band and then the unoccupied conduction band. And such response basically relies on the distortion of wave function. So this can be seen if you recall the basic perturbation theory. So in the perturbation with respect to electric field, your wave function have a correction, and then that correction can be essentially the described by the interband matrix element due to the first order perturbation theory. And this distortion basically moves the electron a bit, and then it can lead to a charge response. And then such charge response from this interband category is closely related to the geometric charge responses. For example, quantum Hall effect and an anomalous Hall effect, and also the polarization current is also this category coming from the interband matrix element and the distortion of the wave function. And such two categories essentially arises from the because we are constraining a wave packet within a single band in the conduction band. So that such a constraint give rise to the so-called geometry of the energy band. And so let us suppose that we have our conduction band, sorry, the valence band is described by this sphere, and this arrow corresponds to the wave function with a specific phase, and then each point corresponds to the each k momentum k for the block electrons, and then the Berry connection is the how this phase changes if you parallelly transport the wave function in the momentum space. So this AK is the Berry connection, and the curvature is the how the base manifold is curved, and then it is quantified by this rotation, the curl of the Berry connection. So so from the block wave function, we can extract this geometric information of Berry connection and Berry curvature, but its physical meaning is clear if we consider the position operator in the K space. So due to the canonical conjugation relationship between R and K, position operator R can be described by K derivative, and since our base manifold or valence band is curved, we need to consider the covariant derivative, which is K derivative plus the connection, and then so this clarifies that Berry connection has some meaning of the coordinate, especially it's called the intracell coordinate in the unit cell. So where the wave function is located in the unit cell is described by this Berry connection. Next, let me briefly introduce how the non-trivial current response arises from the non-trivial band geometry. So let's consider this velocity of the current of the block electron, which due to the Heisenberg equation, it's given by commutator of x and h, and if we plug in this relationship, the position operator is covariant derivative with respect to k and Hamiltonian in the momentum space. If this potential has a gradient along the y direction, we get this commutator between x and y, and then if we plug in this covariant derivative form, this commutator x and y is nothing but the Berry curvature in the k space, and we end up with the current response is given by this so-called group velocity, and then the so-called anomalous velocity term. And this anomalous velocity is the source of Hall effect, because if the potential has a gradient along the y direction, it has a velocity along the x direction, which is a perpendicular direction. And so this is pretty analogous to the Lorentz force in the sorry, Lorentz force in the real space. In the K space, we consider the Berry curvature, and if we accelerate the wave packet, we get the anomalous velocity. And in the real space, we have a magnetic field. If we have a velocity, we have a force, perpendicular direction. So there is a duality between real space and K space, like this. And this anomalous velocity is the source of the well-known anomalous Hall effect, generally seen in the ferromagnets, and like this. And then more recently, there is the anomalous Hall effect in antiferromagnet, which has no magnetization, but shows a huge anomalous velocity due to this typical structure of the spins, giving rise to a big very curvature in this Mangan 310. And so far I talked about how the local curvature of the band structure giving rise to the interesting current response. But the people can talk about the topology if we focus on the how the bands are curved for the full Brillouin zone. So for example, take an insulator, and then we can consider the Brillouin zone, and we can define a map from the Brillouin zone to the wave, the space of wave function, which has generally have interesting shapes like this. And if it has a non-trivial, this mapping has a non-trivial topology, then it is known that there appears a gapless surface state, and also the response is quantized. So the canonical example is the quantum Hall effect, and then quantize the spin Hall effect in the 2D topological insulators. And more recently, there is a discussion on the Majorana-chiral states in the topological superconductors and the Majorana modes in the topological magnets, or like a Kitaev compounds. So these geometry and topology is basically for a ground state of the materials. So my work is about the question about the how this geometry appears in the excited states or nonlinear responses that essentially involves the excited states. So let me move on to the first topic, which is the shift current that arises from the Berry phase effect. Is there any question so far? Okay. So let us proceed to the topic of the shift current. So here we would like to consider the second order nonlinear optical effect, which is that the current is proportional to the E squared. So let us suppose that we shine the light to the sample with a frequency omega 0, and then in the second order we have two effects, which is the sum frequency generation at 2 omega and the difference frequency generation at omega equals 0. And here we focus on this DC current or difference frequency generation. So this is essentially the solar cell action, because shine the light to the sample and then we get the DC current. So the shine the light to the sample and then we can extract the current means that the solar cell action. And in the field of solar cells, one of recent progress is that discovery of the perovskite solar cell family, which is showing rapidly growing efficiency compared to the conventional silicon solar cells. And such a perovskite solar cell is made of this type of oxide with ferroelectric nature. So it has a non-zero polarization in the ground state if we pull the sample, and in this ferroelectric state, if we shine the light, so if we turn on the light, it produces the non-zero photocurrent. And then if we reverse the polarization direction, the direction of the photocurrent is also reversed. So it shows that ferroelectricity and the photovoltaic effect is tied together. So people are interested in maybe mechanism of this type of new photovoltaic effect. And clearly it is quite different from the conventional p-n junction, where we sandwich the p-doped semiconductor and n-doped semiconductor, and then create a band bending like this due to the heterostructure. And then essentially the photovoltaic effect comes from the photo creation of electron hole pairs at this interface, and then they are dissociated due to this band bending or built-in electric field. So on the other hand, such a perovskite solar cell or ferroelectric materials doesn't have any this type of artificial structure or heterostructure. It's just a bulk crystal. So it cannot generate this internal electric field to dissociate the carriers, but nonetheless they produces the non-zero photocurrent. So that's interesting. But since it's non-centrosymmetric or inversion symmetry is broken, it has a non-zero polarization. So polarization basically replaces the role of this type of artificial structure and potential gradient. And one example of photovoltaic effect or DC current proportional to E squared in non-centrosymmetric crystals is known as a shift current. And shift current has been studied pretty much these days, and mostly many interesting research on in a first principle calculations, including the volume titanate, which shows the nice agreement with the theory and an experiment, including the sign change, and also this type of ferrite material. So there are many interesting ab initio calculations on the shift current.
Takahiro, can I
yes.
ask a question? So
Yeah,
what's
sure.
actually change it when you change the polarizations? Does it change the symmetry,
So,
or why does the sign of the current changes?
Yeah, so essentially that's the question I want to answer.
I see.
In a few moments, but essentially, basically, it changes the direction of the polarization in the material, and the current is basically the conveyed by this polarization in the material. So that's why if we flip the polarization, the direction of the electrons are basically conveyed or scattered is reversed, and then it produces the current in a different direction. And then more interestingly, this research by RAP group shows that if we change the direction of the polarization of the light, so there is the linear polarization along the either x direction or z direction, and it also changes the sign of the current.
I see.
So it's really delicate thing. So the first of all, the direction of polarization is essential. It defines the direction of photocurrent, and also sometimes the polarization of the light changes the direction of the current.
Okay. Yeah. Thanks. Yeah.
Yeah. Maybe I can come back to this point in a more from a more intuitive picture.
Yep. Thank you.
So let me. Yeah. Thanks. Let me first advertise a bit of my contribution to this field. Essentially, I developed so-called Floquet theory formalism. So basically, this is a new formalism describing the nonlinear optical effects based on the Floquet theory. And then the Floquet theory or Floquet formalism is basically an analog of Bloch theorem in the time direction. So in the Bloch theorem, there are many bands copied in the k direction, but since the Floquet theory it's time direction analog, we consider the copy in the energy direction. So if we start a valence and conduction band like this, we consider the 1 photon dressed band and a 2 photon dressed band and so on, which is shifted by h bar omega, where omega is the frequency of external electromagnetic field. And if there appears the optical transition, basically these two Floquet bands antitrust with each other in general. And since this is the bands theory, if two bands crosses, there is a small gap opening, and this gap opening is the order of external electromagnetic field vector potential A, and so if you are interested in a steady state in the external electromagnetic field, basically we need to focus on this anti-crossing of two Floquet bands, which is described by this effective Floquet Hamiltonian with the off-diagonal matrix element that opens the gap. And non-equilibrium steady state is essentially basically everything is determined by this anti-crossing of Floquet bands. And if we would like to compute the photocurrent, we can do that by summing up the velocities of occupied Floquet states. But in the one thing is non-trivial, because this is the non-equilibrium system. It's non-trivial how to occupy these bands. We don't occupy all the lower bands. Actually, we occupy this valence band more compared to the conduction band. And then in order to do that, we need the so-called Cauchy-Green's function, which specify the distribution function in the non-equilibrium states. But by doing that, we can get this compact expression of shift current. So this is the expression for the shift current. This is the delta function, which specifies where the optical transition takes place with the frequency h bar omega. And then this is the dipole matrix element and describe the transition rates. So if this combination, the joint density of states and transition rate, this combination is essentially the pieces that appear in the expression for linear conductivity. And for the shift current, we have this so-called shift vector, which involves the difference of Berry connection in the valence and conduction band. And in introduction, as I said, Berry connection is essentially describes the position of wave packet in the unit cell. So this difference means that how the wave packet is displaced or shifted in the unit cell like this. And furthermore, we have a saturation effect like this. The gamma is the impurity scattering rate. So we have this saturation factor, and then this is also this kind of saturation is also a hallmark of shift current. Yes. So Hyun Sik Kim has raised your hand.
I'm sorry for this interruption, but is the shift vector gauge invariant or is it gauge dependent?
Oh yeah, that's yeah. Thank you so much. Yeah, this is very important point. So this shift vector is gauge invariant. So it seems like it's not gauge invariant because Berry connection itself is not gauge invariant, but this combination. So I didn't explain very much, but this phi 12 is the phase factor of interband velocity matrix element. So the extra phase from the gauge transformation for A1 minus A2, it's kind of canceled out with this phase factor phi 12. So in total, this thing is gauge invariant.
Yeah, thank you very much.
Yeah, thanks. So but for simplicity, we can for intuitive picture, we can basically think that shift vector is the difference of two Berry connection and describing the shift of the wave packet in the unit cell for two bands. Okay, thank you so much. So yeah, so this is a more intuitive picture. So in the ground state, since it's we're considering invergent broken system, the wave packet in the valence band has the distribution in some place off-centered like this. And if we shine the light, this valence electron is optically excited to the conduction band, which also have a different position in the unit cell. So with doing this, the wave packet is shifted. So this means that the electron flowing in the direction of the shift vector like this. So basically, in the steady state, this kind of small electron flow is accumulated in time, and it creates the DC photocurrent. So photoexcitation of such electron hole pairs, this has a non-zero polarization or shift vector. And since the current is time derivative of polarization, in the steady state polarization, this kind of electron hole pair creation, occurs many times, and P increases in time. That means that we have a DC current generation, which is shift current. Okay, so this is a pretty cartoonish picture for the shift current. Basically, it is invoked by the non-zero polarization of photoexcited carriers. And then more in an abstract sense, this shift current is arising from or basically measuring the different geometry in the two manifolds. The two manifolds refers to the valence band and the conduction band, because each band forms such a manifold as a K-space. So shift vector is basically the change of local geometry between these two bands. So in this sense, the shift current can be regarded as a geometric nonlinear responses. Okay, so so far we focused on the non-interacting electrons essentially, but next I'd like to ask how does electron correlation modify or even enhance such shift current response?
Before you go on, can I
Yeah.
ask a question? So
Sure.
maybe you know better than me, but the in the experiment, people didn't see people saw the Foucault band formation only like a few times.
Sorry,
Like
which kind of band formation?
The Foucault band, so the formation of the Foucault band.
Oh yeah,
it has been
yeah.
seen only like on the surface of the bismuth selenide and so
Yeah,
on.
it's MIT Nugget experiment.
Yeah, but
yeah, that's right. That's
in other systems, people didn't see it, right? In other cases, people didn't see it, and so is
I
it
think so.
okay?
I think so.
Yeah.
Yeah, as far as I know, the only experimental realization of Foucault band is, the surface of topological insulator.
Yeah. So maybe my question is that so in other cases, people didn't see it. So how safe is it to use Foucault theory to explain this shift current?
Yeah. Thanks. Yeah. So this is basically closely related to the perturbation theory. So
Right.
Foucault theory can always apply. But here, if the external electric field is very weak, essentially the intensity of this Foucault band is very weak, and it cannot, basically experiment cannot capture this very weak intensity Foucault bands. But still, as a current response, we can consider Foucault bands, the contribution of Foucault bands, and essentially that precisely reproduces the result of perturbation theory. If we take the small electric field limit. So actually, so this is the expression I derived from Foucault theory. But if in a small electric field, actually we can drop this saturation effect term, and then this combination is precisely the result, the same as basically the same as the result.
I see.
The second order perturbation theory, like Andre Rapp derived, and also Jones type has derived maybe for the first time.
I see. Okay.
Yeah, so Foucault band itself is really hard to measure in experiment, but still it can be used as a kind of a theoretical tool to go slightly beyond the standard perturbation theory.
I see. Yeah, with that I think I'm okay. Yeah, thank you. Yeah.
Yeah, thanks. Okay, so so let's go on to the electron correlation part. So now next I'd like to think about the role of electron interactions. And in such a strongly correlated matters, there generally appears the collective mode below the band gap, and usually the sometimes external light can couple to the such collective modes. And my idea is that photoexcitation of such collective mode can also lead to the photocurrent, like shift current, and then hopefully it could be giant, because the collective mode basically the gather oscillator strength from the interband transition. So it generally have a giant oscillator strength if it couples to the light. So photocurrent could also be giant. It'll be great. And then maybe one playground with magnets. Magnets has a spin collective modes like magnons. So maybe if we shine the light to the magnet, and then if we can couple the light to the magnons, then they can also lead to the current response or shift current. So that's the basic idea. And in order to introduce the coupling between external electric field to magnon, we basically consider the multiferroics and then electromagnon. Since the multiferroic have a coupling of magnetization and polarization. So since if the polarization can couple to the external electric field, and then it's reflected to the excitation of the magnetization. So magnons also have a polarization and an oscillator strength that couples to the external electric field. And then such property is experimentally confirmed in multiferroics. For example, such electromagnons leads to the so-called dichroism. For example, this material can behave as more transparent from one side, and then if the light doesn't propagate from the other side, for example. So the absorption coefficient is different depending on the direction of the light. So this is the multiferric nature of the material. So now I'd like to use this multiferric nature of coupling of P and M to photo excitation of magnon, and maybe this can give rise to the current response. So in order to demonstrate such magnon shift current, I used a 1D toy model of multiferroics. I don't go to the detail very much, but essentially this is a toy model of ferromagnets like this. And then this is the electron system, and we consider hopping like this, and then there's a staggered potential, and also we want to build a multiferroics. It requires spin orbit coupling, and like this, and then the ground state is tuned to be a ferromagnet with a Hubbard interaction and a spin anisotropy like this. So the ground state is the ferromagnet, and the downspins have a energy penalty of Hubbard U and a spin anisotropy. And let us think about how this ground state is excited and then forms the magnon with a photo excitation. So we start with the ground state with a ferromagnet spin ups, and then we shine the light, and then an external electric field can couple to the spin orbit coupling that hops the spin from one side to the and then it flips the spin and brings to the other side. So here's a doublon which has a larger energy, and then this is a hole here, and then this is pretty big energy, but we can reduce this energy by hopping this upspin to the neighboring side like this. Then we can relax the Hubbard U interaction, but still we have a spin anisotropy energy. So but still this is usually very small energy excitation, because the Hubbard U is very large, but the spin anisotropy G can be small compared to U. And this is essentially the exciton, because the one side has a electron and a hole pair, and but it's a so-called triplet exciton, because the spin is flipped in this exciton. So this is both exciton and also the magnetic excitation, which is magnon. So theoretically, the magnon can be described as a triplet exciton from the this kind of tight binding model approach. Now we can this model support a magnetic excitation or magnon excitation. So this kind of excitation can be studied with a standard Green's function method. For example, X tone can be described by a so-called beta equation in the triplet channel. And then if we compute this, we can get the Magnon dispersion from this ladder summation and taking a pole. So this is the Magnon dispersion. And furthermore, the current response can be derived from the response function. Basically, this is the close to the Kubo formula in the second order. We excite the system, and the electron hole pairs is created, and then it forms a triplet exciton, and then we measure the DC current, and then diagrammatically it can be described like this. And if we really do that, then we can get the shift current spectrum as a function of h bar omega, and then we get the nice peak corresponding to the Magnon excitation. And then here, and I think is that we obtained the current response at the electromagnetic excitation, and I think is that we have a enhancement of the photocurrent from the 1 over omega to the 5th factor. So since this Magnon excitation is lower energy compared to the interband electron hole pairs, this 1 over omega factor greatly enhances. It has a potential to greatly enhances the shift current excitation response for Magnons. Okay, so this is the one example of how strongly correlated electrons show also the DC current generation from the shift current mechanism. Okay.
Takahiro, can I interrupt you? Yeah, could you go to the previous slide? So the graph you drew and the expression in the below, are they the same? So in the below you have only theta peak, right? Yeah, but the
it's actually different. This is the full calculation, including all the dispersion. So I was very quick, and then actually I omitted many things, but this is the full calculation, including this Magnon structure and band dispersion of the original tight binding model. But here is this is basically a very crude approximation for this full spectrum. I assume the flat band dispersion and a flat Magnon dispersion and so on. And then I basically extracted the weight of this Magnon peak with this. But basically this should be broadened by such a dispersion relationship.
I see. And is there any Berry phase physics going on in the 1D model or not?
Yeah, well, so that's the question I was expected. But basically the physics is the same as the this shift current from the interband, which has a shift of the wave packet, and it creates the current. So basically the photo excitation changes the position of the wave packet, and then produces the photocurrent. So now in the case of electromagnons, Magnon has a non-zero polarization. So according to this experiment, Magnon itself has a non-zero polarization. So if we excite Magnons more and more, so we can replace these electron hole pairs with the Magnons. So the photo excitation is more and more Magnons that have non-zero polarization. Then the polarization increases in time, and then that leads to the DC photocurrent. So actually, I couldn't describe this polarization of Magnon with respect by using the Berry connection, but but clearly there is a relationship. So the polarization of electron hole pairs, it has a Berry phase formula, but here it's a Magnon collective excitation. So it's basically the averaging the Berry connection for the many states that participate into the Magnon excitation.
I see. So it could be a little bit more subtle to
Yeah,
point out with.
yeah, I agree. So it could be more subtle.
Mhm.
Yeah. But essentially the mechanism is the same. So if we compute this bubble diagram without this
Mm.
magnum propagator, just bubble
Mm.
diagram, that produces the shift current with a barrier connection
Mhm.
difference. But if we
Mhm.
include this beta salpeter part, we
Mm.
get the magnum shift current.
I see. Good. Yeah. Thanks.
Yeah, thanks so much. Yeah, that's an important point actually. Thanks so much. So in the last 10 or 15 minutes, let me switch to another topic, which is the non-reciprocal Landau-Zener tunneling. So this is essentially the directly the same. So how the geometry and topology appears in the nonlinear response, and the shift current was a nonlinear optical effect. So the electric field is basically the light, and it was AC field. But now we like to talk about that external DC electric field, which is nonlinear transport. So instead of shining the light to the sample, just apply a strong electric field to the sample, and then the such in that case nonlinear response is called a so-called non-reciprocal transport, uh, and this nonlinear IV characteristic appears. I like to seek a geometric effect in such a nonlinear transport regime. And so typically, this nonlinear transport is a rectification effect that can be found in diode devices. So in the Ohm's law, J and current is proportional to the voltage or electric field. But we also consider the E squared term. Then the IV characteristic is this kind of curve, and then and at one side, electric current can flow more easily, and then on the other side, current is very difficult to flow. So this is basically the diode effect, which also uses the interface of p-n junction, and then the width of this kind of depletion region is grow and become thin and so on. So this is known for this kind of heterostructure. So and then the people are more in, in condensed matter context, people are recently more interested in the bulk nonlinear transport. And a typical example is nonlinear transport with time reversal braking, and then called magneto-chiral anisotropy, which is current proportional to E squared and also proportional to external magnetic field. And then this is essentially the change of resistivity under B, or magnetic field. So one interesting example is kind of a helix. This is the bismuth helixes, and it's kind of solenoid. And if we put the magnetic field, and then depending on the current direction, the induced magnetic field is either parallel or anti-parallel in the external magnetic field threading this solenoid. And according to this parallel or anti-parallel nature, the resistivity can be largely changed, and that's known as a magneto-chiral anisotropy, and then measured in the bismuth helices, and also some organic compounds and the silicon devices. So this kind of nonlinear transport in bulk materials with time reversal broken system is known. But now I'd like to ask such non-reciprocal transport or diode effect in bulk crystals without time reversal symmetry. Is this possible? So this is the question I'd like to ask. And the two actually I'd like to demonstrate this is true in such a tunneling problem setup. So maybe you know the so-called Landau-Zener tunneling. So it's an insulator with an energy gap, and if we apply a strong electric field to this type of wave packet, this is driven in the band structure, and then if we do it very slowly, it goes down. But if you go quickly, this can be tunnel into the conduction band, and this is called Landau-Zener tunneling in the diabatic limit. And people usually consider this Landau-Zener tunneling probability P. And it is known that this tunneling probability is a non-perturbative effect, which is proportional to exponential minus 1 over e. So if we Taylor expand this expression at e equals 0, all the coefficient becomes 0. But nonetheless, we have a non-zero response for stronger e with a threshold behavior. So this is non-perturbative. And the picture is something like this. So in the real space, there is a band gap, but in the presence of electric field, this band has a slope in the real space. Then this wave packet can tunnel through the this band gap, and the tunneling distance is typically delta over e, where delta is band gap here. And the typical wavelength is V over delta. So these two ratio determines the tunneling amplitude. Basically, the 1 divided by 2 give rise to this exponent here nicely. So now let us apply this Landau-Zener formula to non-reciprocal transport. Then now we can easily see that it fails to capture any non-reciprocal transport, because it only essentially depends on the band gap of the system. If time reversal is present, this band dispersion is symmetric at k and minus k. This probability, tunneling probability, cannot be changed for E positive and E negative. So Landau-Zener formula gives only reciprocal transport for positive E and negative E. So what is missing here? The missing factor is the Berry phase that we have been discussed. So in the invergent broken system, there generally appears such a geometric phase like a Berry connection, and this kind of a geometric correction to the dynamics of a wave packet can lead to the shift current in the previous case. So maybe we need to incorporate this kind of a geometric phase effect. So in order to do that, we kind of generalize the Landau-Zener formula. So we are doing the perturbation theory, our adiabatic perturbation theory. We basically expand the wave function with a valence electron and valence and conduction wave function like this with a dynamic phase, and also we retain the Berry phase here, and then we put this wave function into the Schrödinger equation. Then we get for tunneling amplitude, we get a geometric phase factor like this. This is essentially the same as the shift vector, because it's a difference of Berry connection, and this is the same as the phase of interband matrix elements. Then the tunneling amplitude can be solved perturbatively with respect to this this term, and then we get this phase factor, and and then here the k integral is running from the minus k infinity to plus k infinity, and then now the standard prescription is we analytically continue this band structure into the complex k plane, and deform this phase factor, and then this basically we can do the saddle point approximation for this phase factor, and then the saddle point appears at the gap closing point that locate in the complex plane away from the real axis. And then if you do this carefully by keeping this geometric factor, shift vector, we obtain this generalized Landau-Zener formula, where the tunneling amplitude is given by a conventional band gap over E expression, and also the geometric correction. This is essentially the same as the shift vector. Now, this geometric correction turns out to create the non-reciprocity, because for positive E and negative E, actually the saddle point changes whether it's in the upper plane, half plane, or lower half plane, because this amplitude should be the exponent should be negative to behave as a tunneling amplitude. So if we, for positive E and negative E, we basically change the saddle point, two saddle points. Then this geometric factor actually changes the sign according to this change of the saddle point, and this leads to the tunneling rate difference for left and right direction, and then this is nothing but the non-reciprocal tunneling. And we demonstrated with the 1D toy model, so-called Rice Melee model, and clearly we can get the conventional Landau-Zina type term and also the Berry phase term that depends on the sign of electric field, and then it shows the non-reciprocity. So if we plot the tunneling probability is different for positive E and a negative E. And also these two curves have the same threshold behavior. This is also non-perturbative, but that they have a different tunneling amplitude. So finally, maybe we like to consider the meaning of this geometric factor in the tunneling problem. So as I said in the previous topic, the shift vector is basically the difference of the position of the wave packet in the unit cell. So this matters when the interband tunneling occurs, because for example in the positive E, if we in the ground state, the wave packet is located at the blue position, but if this guy want to tunnel through the band gap, it turns into the conduction band, and the position of the wave packet is slightly shifted by R. So in this case, this red wave packet is within this the conduction band limit. It should travel the more distance by R, because there's some position is cancelled by the shift vector. And in the other case, this wave packet is shifted by R, so this only need to travel shorter distance by R, because if this guy transition into the interband, the wave packet position is automatically shifted by R, so it can gain extra R from this interband transition. So it just need to travel shorter distance, and so the tunneling distance is modified by shift vector depending on left or right. So that's why tunneling probability and it shows a non-reciprocity depending on positive E and negative E. And furthermore,
short question.
Sure.
The Berry connections you introduced, does it break the reflection symmetry, or?
It breaks the reflection symmetry.
And then what you're saying is that the breaking of the reflection symmetry is not enough to generate the non-reciprocities, and I need the Berry connections. Is it right? Or is it enough to break the?
Once you break the reflection symmetry, generally there appears the Berry connection.
Right. Okay. Yeah. Good.
Yeah. So it's connected. So inversion breaking and then Berry connection. So they're kind of two closely tied things.
Right.
So yeah. So basically I'm using that property.
Yep. Thank you.
Yeah. Sure. And then this is the final slide. So in the steady state, even we can there emerges the non-reciprocal spin current or spin transport. So this is our new paper last week. we put in the Landau-Zener problem, we added the Rashba spin orbit coupling. Then the band structure is spin split like this with a spin orbit coupling. And since the tunneling direction or tunneling amplitude is different between left and right, and the left and right are also coupled to the up and down component of spin. So so this reciprocal tunneling, we can induce the nonlinear spin transport. So this is the spin current when the electric field is applied to the right. Then more upspin is created by tunneling, and then more downspin is created. So generally, if we add a spin orbit coupling to this kind of nonlinear Landau-Zener setup, we can get the spin current or spin accumulation. And this is kind of related to the experiment of DNA with a strong electric photocurrent of the DNA traveling through the DNA is known to show some spin accumulation. So this is kind of analogous. So the tunneling electrons in the some helical material can create a spin current or spin accumulation. So to summarize, I introduced the shift current, which is an example of a geometrical nonlinear response, and I introduced the formulation by Floquet theory and a Magnon shift current. And then in the second half, I talked about the non-reciprocal Landau-Zener tunneling, and I demonstrated non-reciprocal charge and spin transport from Berry phase. And this is the outlook. This is the really final slide. So there could be a more diverse geometric nonlinear effects, especially in strongly correlated systems. For example, superconductors or Monte insulators would be interesting playground. And also there are recent experiments are showing more and more controllability in heterostructure materials. So that will be also interesting playground to look at the nonlinear optical effects. So thank you so much for your attention.
Thank you. So the session is open for the questions, comments.
Yes.
Yeah.
Okay, yeah, thank you very much for your talk. So
Yeah,
I
thanks
have
so
a
much.
question about the second part.
Yes.
So, I mean, when you have this reciprocal Landau-Zener tunneling, so can this be just equated to having some local electric field? Additional local, I mean, spontaneous local electric field in your system? I mean, you talked about breaking reflection symmetry. So if
yes, that's right. Yeah, it's the system has a broken reflection symmetry. So, for example, I took this Rice-Millet model. This has a non-zero polarization, depending on these parameters. So typically it has a direction of particular direction of polarization. So in the last this cartoonish picture, you can also think that this wave packet is kind of driven by the internal polarization. So maybe polarization can help the tunneling, or it's against the tunneling. That changes the tunneling distance and then the tunneling amplitude.
Okay, thank you.
Yeah, thank you. Yeah, that's a good point, I think.
Other questions, comments? I have very naive questions. So you mentioned the key-type material there in the introductions, right?
Yes.
And I wonder if the nonlinear effect can introduce some interesting effect in the thermal Hall too.
Yeah, that's right. Yeah, actually, I wanna think about that. So so key-type material, maybe thermal, maybe for example, nonlinear thermal conductivity. It would be an analog of shift current in magnetic materials. So the only thing that we need for shift current is basically that inversion braking. Let's see. So maybe one can break one can consider the inversion broken kind of analog of key-type magnets, and then one can compute the nonlinear thermal conductivity.
Right.
With maybe you can maybe DC temperature gradient or AC temperature gradient. It depends, but that could be also a directionality to the thermal transport. Yeah, that would be interesting.
But I'm not sure if it can be done in the experiment. I mean, to measure the nonlinear part. That's
Well,
a different
if it's
yeah.
non-reciprocal heat response, that could be
Right.
measurable. So maybe AC version it would be slightly difficult, but yeah, for example, this kind of thing. So that the temperature gradient, positive and negative, and the heat current could be different. That will be a easier setup, and then even this kind of DC setup, there is a chance that can measure the local Berry connection or Berry phase. So maybe one could do a kind of Majorana construction for models with inversion braking like this, and then compute the nonlinear thermal conductivity.
Right.
Yes.
Yeah, could be cool. Yeah.
Yeah, it will be cool. Yeah.
And then I also have questions on the Rice-Miller model that you introduced. I guess Rice-Miller model, it's hard to find the material. I don't know, but can I use TMD material, like which is already gapped Dirac fermions? And then
Rice-Miller model is basically the 1D model for general ferroelectric materials, but for 2D, maybe TMD will be maybe easiest most typical inversion broken model, I guess. It's just a Dirac fermion plus energy gap at the minimal level, and that breaks inversion symmetry. And then it is known that the shift current is non-zero for TMD. But actually, interesting is that the shift current of TMD has never been measured. It's not it's C3 rotation symmetry, so it's not polar material. Somehow it seems that difficult to measure the shift current response for non-polar but inversion broken materials like TMD.
I see. There is a question in the chat.
Oh, really?
So yeah, I think it's related, but yes, it's from Jeter Shin from Seoul National University.
Chat. Oh, chat. I see. Yeah, okay. In the case of the non-reciprocal spin transport, the Rashba system has spin moment locking with in-plane spin polarization. Can we expect this type of Oh yeah, that's a cool question. Yeah, I actually I guess out of plane spin polarization, that's also can lead to some non-reciprocal spin transport, definitely. In my modeling, here I just use the simplest spin orbit coupling in order to make my analysis the simplest. But definitely, so out of spin polarization, like a Dressel house type spin orbit coupling, and I think this is more realistic situation, and definitely I believe there could be some similar non-reciprocal transport like spin, either spin or charge, and I think it's very interesting to study this kind of more general type of spin orbit coupling. Does that answer your question? Oh, okay. Thank you. Yeah, thanks so much for your question. Yeah, that was great. Another question in the chat box. Is there any known nonlinear response distinguish topology of the material? Oh, that's interesting. I mean, topological trivial, non-trivial material measure shows a different response. Yeah, I think so. So far, I was talking about the local kind of geometry rather than the global topology, because the shift vector is just the difference of Berry connection at some particular K point that participate in the optical transition. And in order to distinguish the topology, we need to look at the global connection of those geometric quantity. I think one example that I know that the topological nonlinear optical effect is so-called circularly photogalvanic effect, circular photogalvanic effect in Wallstein metals. It is known to be quantized. Actually, I and Fernando de Juan and then Adolfo Grushin and then Joe Moore discussed that kind of effect. So that the I guess I have a slide here. Maybe no. And that so the one example that I know is quantized CPG. That CPG is basically the shine the circularly polarized light. So let's see. Yeah, here shine the circularly polarized light instead of linear polarized light. Then measure the DC current. And in Wallstein metal, that photocurrent is known to be quantized, and related to the topological charge of the Wallstein metal. So yeah, that's one example that I know, and then it would be great if there is another other such topological nonlinear responses. Okay. Okay. Yeah. Thank you.
Other questions, comments? If not, I think we learned a lot from Takairo's talk today, and then the time is already went by roughly 10 minutes. So I think it's time to wrap up. So I would like to thank the speaker again. And yeah,
thanks so much.
The session is over. And Takahiro, thank you. And please drop by Korea next time after the
sure.
coronavirus is gone.
I'd like to, and I like to have a fugu sashimi.
Yeah, or you can bring your family too. I would be happy
that would be great. That would be great. Yeah.
Guide around Seoul and
that would be great.
Yeah.
Thank you, Gil, for inviting me. It was a great fun.
Yeah. Okay. I gotta leave to another seminar actually. So.
Okay. Good. Yeah. Thanks so much.
Yeah. Bye.
Okay. Bye.